Hey, and welcome to Gaffy's Grinds. In today's video, we're going to do a walkthrough of a question 11. It's from the 2016 higher level paper. Right, 2011 usually has 3 parts and you have to choose 2. For the sake of this video, I'm going to go ahead and choose parts A and B. Part A is a pretty standard stoichiometry question. So if you like maths, if you like the stoichiometry questions, working with moles, converting to grams, working out limiting and excess reagents, then this is the type of question that you would enjoy. If not, but you're still good at it, doesn't matter whether you enjoy it or not, you have to play the game. Are you good at this? Are you good at this style of question? If so, then this should be your target in the exam. And the second one is about shapes of molecules, Vesper theory, different types of intermolecular bonding, and how that affects melting points, boiling points, etc. Right, so those are the 2 parts. So if you want to have a quick revision of these 2 areas now, I would say grab your notes. If you're my students, you can have a quick flip through your summary book, the Chemistry Essentials Unfolded, or indeed your notes and the booklets that we've gone through. If you want to do that, pause the video and do that now. Apart from that, you're going to need a calculator, a pen, and it's a good idea if you have your exam papers to work along with me. Right, so what I'm going to ask you to do is we're going to look at part 8, so it's like stoichiometry part. I'm going to ask you to pause the video. I'm going to ask you to have a very careful read from here to here. Do that now, please. All right, so again, at this stage now, you have an opportunity to pause the video and highlight anything that you think is important here in the question. Pause the video and do that now. All right, so what I'm seeing here is I've got a chemical reaction and I'm going to be looking at the stoichiometry. So when I'm looking at the stoichiometry, I'm interested in the reactant ratios. Okay, so as I can see here, this is a 4:5:2:2:5. It's a good place to start is by writing down the reactant ratios. And remember that those are the molar ratios. That's only for comparing the number of moles. And then at this stage, is there any quantities in the text that we can match with the chemicals in the equation? So pausing the video and seeing can you match them up now. Okay, so hopefully it says that one of the 2. It says here that one of the 2 reactants is in stoichiometric excess. That means we have more than we need of it. When we have 20.2 grams of potassium nitrate. So I'm looking at my equation. Which one is the potassium nitrate? Well, I'm seeing potassium K, nitrogen 8, potassium nitrate. So I'm just going to summarize that in my KNO3 here, I know is equal to 20.2 grams. Okay, and it says it reacts with 24 grams of sulfur. Oh, sorry, that's not what I meant to do at all. Where's my highlighter gone? Oh, I'm just going to underline it. Sorry, I messed up my highlighter. Sulfur. Okay, so we've got sulfur is equal to 24 grams. Okay, and the first question is asking us which reactant is in excess. Okay, now of course we can't tell just by looking at the grams. Yes, there's more grams of sulfur than there is of KNO3, but that's not how we figure that out. We have to figure it out using moles, okay, and using the reactant ratio. So what I'm going to do is I'm going to ask you to pause the video and work out now which reactant is in excess and what mass of this reactant is unused at the end of the reaction. So some of you guys will be able to have a go at doing that now. So having a go, pausing the video and having a go at that now. Okay, so this is part 1. And the correct answer here was sulfur. Okay, and how much was left over? You should have got 16 grams of sulfur was left over at the end. Okay, so if you got that, well done. If not, I'm going to ask you to pause the video and have another go now that you know what the answer is. All right, so hopefully you managed to get to the answer, the final answer. If not, then you need to work with me to figure out what's going on here. The first thing we're going to do is work out how many moles of each of these we have here. Okay, we know that from the balanced equation, we should have 4 moles of KNO3 for every 5 moles of sulfur. That's the reactant ratios that we have here. All right, so I am going to begin with the KNO3 and I'm going to find out how many moles we have. Okay, so we're going to write down what we have. We know we've got 20.2 grams of KNO3 and I want to know how many moles that is. So what I'm going to ask you to do now, if you weren't able to do this by yourself, is pause the video and convert this to moles. Okay, so what we should be doing using the conversion factor here is find out how many grams of KNO3 we have in every mole of KNO3. Okay, and so we're going to pause the video and work this out now. For every 1 mole, how many grams would there be? Okay, so when you work out the molar mass of KNO3, you should have got 101 grams per mole. Okay, so once we do that, we should get 0.2 moles. Okay, of course, the grams of KNO3 cancel out, and we're left with moles as our units, and I get 0.2 moles of KNO3. So the next thing you want to do is work out, well, how many moles of sulfur are there in 24 grams? So 24 grams of sulfur, pause the video and work out how many moles that is now. Do that now. Okay, so for sulfur, it's grams of sulfur in moles of sulfur. So we want the grams to cancel, and we know that for every 1 mole, there are 32 grams of sulfur. That's hopefully what we got. This is an element, so it's pure sulfur. Go to the periodic table, you find the molar mass is 32. And when we do that, we got 0.75 moles of S. Okay, so that is how much we had at the start when we weighed out these grams, of course. But is that the final answer? Just because this number is more, does that mean that it's in excess? We're not sure yet, because this is the ratio that they react in, 4 KNO4s to 5 S's. Okay, so at this stage, we have to think about those ratios and find out, okay, well, if we had this many moles of that, how much of the other one would I need to react with? So you can choose either of these, either choose this one, number 1, or choose this one, and find out if I had that much of this one, how much KNO4 or how much sulfur would I need? Or if I had this much of this one, how much KNO4 would I need? So if I started with the sulfur, how much KNO4 would that react with? If I started with the KNO3, how much sulfur would that react with? Okay, so pause in the video and either choose one of these and work out, according to the balanced equation, how many moles of the other one would I need to react with. Pause the video and do that now. All right, I'm going to go ahead and I'm going to choose this one. Okay, and I'm going to say, right, well, if I had this much in the beginning, 0.2 moles of KNO3, how much sulfur would I need to react with? Well, I'm going to say, looking at my balanced equation here, I'm going to say that for moles of KNO4, I have 4 moles of KNO3, sorry, I keep saying KNO4, for every 5 moles of sulfur. That's what my ratio tells me, 5 moles of S. So moles of KNO3 is gone, and I'm finding out how many moles of sulfur that would be for 0.2 moles of KNO3. 5 over 4. Okay, and that gives me 0.25. 0.25 moles of sulfur is all I actually need. Okay, so if I start with this much KNO3, I only need 0.25 moles of S to react. So there I can clearly see that there's way more sulfur than I need. Okay, so I'm writing a sentence at this stage. S is, I'm actually going to start moving this way over the page, sorry, just so I don't take up too much room. S is in excess. Okay, there's more than enough. The 0.75 and I only needed 0.25. Okay, so S is in excess. And then the second bit, it says to what mass of this reactant is unused at the end of the reaction. We don't know what mass is unused at the end of the reaction, but we should be able to see how many moles are left over. So hopefully you can see that I've got 0.75 moles. So work out how many moles are left over of S. Pause the video and do that now. Well, of course, I use this much. So take away 0.25 moles of S. So that's going to give me 0.5 moles left over of S. Okay, so the next question is, well, what mass of S is that? So pause the video and working out what mass that would be. Doing that now. Okay, so hopefully what we're saying here is that 0.5 moles of S times by how many grams of S are there in every mole. So we already did this earlier. It's 32 grams of sulfur for 1 mole. Moles cancel out, and that should give me my answer in grams. Okay, so pause the video and do that now. 16 grams of S left over. Okay, so that was our original answers. Remember, I told you what the answers were. Yeah, I thought I wrote them down, but I must not have. Sulfur's in excess, and there are 16 grams left over. Right, so that's part A done for 13 marks. Remember, guys, when I ask you to pause, you have to pause and try and do it. If you're just copying what I do, you're lying to yourself, and that's really not going to help you when it comes to being able to do these questions by yourself. All right, we're good so far. Let's see what the next bit is. It says calculate the total volume in liters of the gaseous products measured at STP formed in the reaction. Okay, so first of all, let's pause the video and identify which products are gases. Okay, so I see a gas here. That's a gas product. A gas product here. Okay, so what I want to know is, well, how much in liters of gas was produced altogether? Now remember, what is the limiting reactant here? The limiting reactant is this one here. This is limiting. We know this because the sulfur is in excess. So this here is the number of moles that we start the reaction with of the limiting reagent. So I have to start with this reactant here. The limiting reagent is this one, 0.2 moles. And once we know we started with 0.2 moles of this, we can work out how many moles of the product we will produce based on the reactant ratios. Okay, so what I need you guys to do is pause the video and work out, first of all, how many moles of each gas product were produced here according to this equation. How many moles were produced of each gas product? And if you can then work out how many liters at STP each of those would take up. Pause the video, do that now. Okay, so first of all, we're going to start with 0.2 moles of KNO3, and we want to find out the nitrogen first of all. Okay, so if we start with that many moles of KNO3, what I want to know is, according to the balanced equation, how many moles of N2 would I make? So moles of KNO3 on the bottom, they're going to cancel there, and we're going to find out how many moles of N2 were produced. Okay, so according to the reactant ratio, there are 4 moles of KNO3 for every 2 moles of N2. That's what the ratio says, 4 to 2. Okay, so when I do that, I'm going to get 0.1 moles of N2. Right, what about when I start with 0.2 moles of KNO3? How many moles of SO2 do I get? Pause the video and work that out. If you haven't done it already, you've got to take over, you've got to do some of this. Okay, so again, I've got moles of KNO3 down here and moles of SO2 up here. KNO3 cancels out, and according to the equation, there are 4 KNO3s for every 5 SO2. So 4 KNO3, 5 SO2. Pausing the video and working that out now. What you should get here is you should get 0.25 moles of SO2. Okay, so you can do these separately or you can add them together because they're both gases. Okay, so we have 0.35 moles of gas. So if we add them together, all together, the total products equals 0.35 moles of gas, moles of a gas. And what we want to know is, what will the volume of that gas be? So converting moles of gas to liters of gas at STP. So pausing the video now and working your way down to liters of gas. Pause the video, do that now. Okay, so what we should be getting here is, well, we know if we had 1 mole of gas, 1 mole, that would give us 22.4 liters at STP. So when we get this, we got 0.35 of a mole times by 22.4, and that gives us 7.84 liters. So altogether, this reaction will produce 7.84 liters of gas. Excellent. Now on to the last bit here. It says what mass of solid is produced. What mass, so that's going to be in grams, of solid is produced. And up here, I see that the only product that's a solid is this one here. Okay. All right, so again, we start with the limiting reagent, the KNO3, find out how many moles of K2O would be produced, and then find out how many grams that would weigh. So pause the video and walk through that now. Right, the answer here, the correct answer is 9.4 grams of K2O. So if you got that, then you did it right, well done. If not, again, pause the video and watch me doing it here, okay? 1, 2, 3. All right, so we've got 0.2 moles of KNO3. And then we want to find out how many moles of K2O that produces. So this is moles of KNO3 on the bottom and moles of K2O on the top. Okay, they cancel and we get moles of K2O. Look at the equation again here. What is the ratio? Pause the video and write them down. Okay, so I'm seeing here, I've got 4 of these for every 2 of these. Okay, so that's going to give me basically a half, 0.1 mole of K2O. All right, and then we want to take that 0.1 mole of K2O and we want to convert to grams. So pause the video and everyone should be able to do that now. We've all done moles to grams loads and loads of times. All right, pause the video, doing it. Okay, so for moles of K2O, how many grams of K2O are there? Okay, so every 1 mole of K2O, moles of K2O cancel, leave me with grams of K2O, and my molar mass is 94. Okay, so your answer here is 9.4 grams of K2O. Right, well done, guys. That is, again, if you like the maths, that stuff is really easy. If you're good at the unit analysis, I think that question is not a bad question at all. You can think your way through that. The only issue maybe would have been where when you've worked out your limiting reagent or when you've worked out your excess reagent, finding out over. But then knowing that when you're trying to find out how much product was made, you have to use the limiting reagent because that's the one that decides how much of the products can be made, not this one. If you use this number here, you're going to have way too much product produced. You can't produce that because this one here will run out way quicker. So you have to use the limiting reagent when you're finding out how much of the products were made. We went through that very carefully when we were doing this theory the first time, but you can see how people might have forgotten that. So it's good to practice that and remind ourselves. Right, on to part B now. Okay, on to part B, and this is more theory-based. So this is the kind of thing you would like if you maybe don't like the numbers as much. So what I'm going to ask you to do is pause the video and have a read from there down to there. Okay, so hopefully you can see you've got 3 fairly similar formulas here, considering the 3 gaseous hydrides. Okay, hydride just refers to the fact that they all have hydrogen in them. Okay, they're all bonded to hydrogen. But the middle atom is different. Okay, this one you've got nitrogen, this one you've got phosphorus, and this one you've got astatine. Okay, here's the different names, and here are the properties. How are the boiling points affected by the different molecules? All right, so it says here using the form data in the formula tables, and so in other words, log tables, determine the type of bonding arsenine is expected to have. Okay, now the type of bonding we're referring to is the bonds within the molecules. Okay, the intramolecular forces. Okay, so what are the options here? You're either going to be covalent, polar covalent, or ionic. Okay, so I'm going to show you the tables here, and remember which one we're looking for. It says the bonding arsenine. So that's this one here, the bottom one, astatine with hydrogens. Okay, so you've got 3 ASH bonds. Okay, so ASH is the bond, and there's 3 of them, so they're all the same. So what type of bond is that basically? All right, so I'm going to throw up the log table for you. And we're going to show you the page you need. Okay, I'm going to stop now. I'm going to ask you if you know how to do this with your log tables. Pause the video now and go and do this, find out the bonding before I tell you which page you're supposed to go to. Okay, so you should only be playing if you've had a go, if you're able to. If you're not sure where you need to go to the electronegativities. Okay, so I'm flicking through here. I'm looking for the periodic table pages. I think it's up around page 80. So I'm flicking through all the math stuff. We don't need any of this. In chemistry, we're really focused on only a specific couple of pages. Here they are. So we're looking for the ones with the electronegativities. This is the page you want. It's page 81, okay? And now using this table to figure out the bonding. Pause the video now. Okay, first of all, where's astatine? Here it is here. Where's hydrogen? Here it is up here. They are the two elements in arsine. Okay, so what I want you to do is work out what type of bonding we would have. All right, so back to our question now. Okay, back to our question. So arsine, we want to find out what type of bond does the A or H bond, because that's the only bond in here. There's three of them, A or H. There's three of those type of bonds. Well, arsenine was 2.18 in electronegativities. Hydrogen was 2.2. We find the difference between them, guys. Pause the video, find the difference. 0.02, okay? And that falls into our range where it's less than 0.4. And what does that mean about these bonds here? What does that mean about this? Okay, well, what that means is that the electrons are shared equally in the middle of this bond. So it's not a polar bond. So this is what we call non-polar covalent. So that's what we were looking for there in the first question, non-polar covalent. Well done if you got that right. Now what it says is draw a dot and cross diagram using the valence electrons. So it's a covalent dot and cross diagram to show the bonding in arsine. Predict the shape of the arsine molecule. So predict the shape and draw the correct diagram. Okay, so I'll put back up the periodic table again for you so you can see what group arsine is in, or what group astatine is in, sorry. Sorry, where is this? Yeah, here. All right, so I'm just going to put up your standard periodic table this time. You want to see what group astatine is in and hydrogen is in. And from that information, pausing the video and doing that now. Okay, if you're not sure, well, astatine is in group 5. Okay, so that means it's got 5 valence electrons. And it's going to combine 3 covalent bonds with 3 hydrogens. Okay, so what I need you to think about is how many bond pairs do you have? Do you have any lone pairs? And how will those lone pairs affect the shape? Pause the video and do that now. All right, so what we should have figured out here is I'm just going to go back. Sorry, no, I just need to, I think my screen is freezing here, so I'm just going to pause for a second. We're back. Okay, so with arsenic is in group 5, which means it's got 5 valence electrons. It's it's astatine, sorry, it's AS. It's in group 5, which means it's going to form 3 covalent bonds with the 3 hydrogens, like this, 1, 2, 3. But it's also going to have this lone pair up top because it's got 5 valence electrons. So this here, I'm just going to label it as lone pair. So this here is a lone pair, and you should have this to get the diagram correct. And then, of course, it's forming a covalent bond, which is a shared pair of electrons with 3 hydrogen atoms. Okay, so that's what we should have done. Then what you need to do is name this shape. So name this shape, predict the shape. Pause in the video, doing that now. And what you should have said is that this here is called a pyramidal shape. Pyramidal. It doesn't ask for the bond angle, so we don't need to give it here. Okay, it does not ask for the bond angle. We do not need to give it. If it did ask for the bond angle for this, and you pause the video and write down what it is. Okay, so the bond angle for this would be 107 degrees. Okay. All right, so let's look at the next bit. Which, if any of the 3 hydrides, would you expect to have intermolecular hydrogen bonding? Which of them would you expect to have intermolecular hydrogen bonding? It could be 1 of them, it could be 2 of them, it could be 3 of them, and justify your answer. Pause the video and write that down now. Do you expect any of them to have it, and which one? Why? Justify, give a reason why you picked that one. Okay, and you notice that this question is not broken into little pieces, so you have to be very careful here. There's lots of little sections, and you could miss one fairly easily. So I always say kind of maybe make bullet points down the side everywhere where there's a new question. Right, so which of these three hydrides would you expect to have hydrogen bonding? Okay, well, it definitely can't be this one or this one. Okay, and the reason for that is that they don't have hydrogens which would be bonding next to in the next molecule to a nitrogen, oxygen, or fluorine. So let's say the first one here, ammonia, looks like this. If you have delta positive hydrogen atoms, then they could potentially form a hydrogen bond with a delta negative nitrogen atom on the next molecule. Because remember, for hydrogen bonding, you have to have a hydrogen that's delta positive, and it has to be bonded to either an N, O, or F. And these don't have those. This has P's and this has AS's. So it definitely can't be this one. It definitely can't be this. Okay. So let's turn that into an answer here. Okay, so which one would expect to have hydrogen bonding? Give an answer and justify. Pause the video, do that now. Okay, so the ammonia is the answer, ammonia, or you might have said NH3. And the reason for that is that we have a nitrogen, which is delta, or we'll probably say a delta negative nitrogen atom can H bond with delta positive hydrogen atoms. Okay, now the others don't have that. Okay, so because the ammonia NH3 has the nitrogen atom, then that's going to be hydrogen bonding. The others will not. Okay, so there is answered and justified. Next one, suggest the reason why ammonia has the highest boiling points of the three hydrides, and why is phosphene's boiling point lower than that of arsine. Okay, so pause in the video and having a go at parts 1 and 2 there. Why is ammonia the highest boiling point? Pause the video. So NH3 highest BP. BP, why is that? Pause the video and write an answer now. Okay, well, this is the one with the hydrogen bonding. Okay, and hydrogen bonding is much stronger than what the others have. The others either have dipole-dipole, or they may only have van der Waals forces. So again, this is non-polar covalent, the arsine, so this will have van der Waals forces. Okay, and then for phosphine, we'd have to work out what that has. We might have to do that in the next bit. But hydrogen bonding is stronger. I should probably say hydrogen bonding in ammonia. In ammonia is stronger than what either of the other two have. Stronger than the other intermolecular forces. So this is what makes them have a higher boiling point forces. I should say intermolecular forces. Okay, and then the last question says, suggest a reason why, what does it say? Phosphene's boiling point is lower than that of arsine. Okay, so we're looking at phosphine. Well, we know arsine has van der Waals forces. Okay, we know that van der Waals forces, which are the weakest. So phosphine, it says, has an even lower boiling point, and we can see that. Okay, so this is minus 62.5, which is a low boiling point, but this is minus 87.7, so that's even lower. So what's the difference between these two molecules? Okay, but if you go back to your periodic table for a second, you can see that both of these molecules have their central atom in the same group, nitrogen and phosphorus. So just going to have a little look here. It's gone. Just trying to get down to the periodic tables. Look at your periodic table too and see what I'm on about. This now. Nearly there. This is there we go. Okay, so looking at nitrogen and phosphorus are in the same group, and so is arsenic, right? Nitrogen and phosphorus and astatine are there. Sorry, these are the two central atoms. And they're both the same. We have P and we have AS, and they're surrounded by 3 hydrogens like this. So they both are non-polar, which means they both have van der Waals forces. So what's the difference between these that could mean that astatine has a higher boiling point? The one that has astatine has a higher boiling point. So pausing the video and suggesting a reason for this now. Okay, so hopefully you remember that van der Waals forces are caused by just electrons moving inside the atom. Random movement of electrons creates tiny temporary dipoles. And the more electrons we have, the stronger the van der Waals forces are going to be. So because astatine is a bigger atom than phosphorus, it has more electrons. So it has more moving electrons. So more moving electrons. And this creates, therefore, stronger van der Waals forces. Van der Waals forces. Okay, so slightly stronger, which is going to affect the boiling point. So back to the question. Can you now write that down and give a reason why it has a, give a reason why phosphene's boiling point is lower than that of arsine. Pause the video, write that down now. Okay, so hopefully what we're saying here is that phosphine has a lower boiling point than arsine because, okay, so arsine contains astatine, and astatine is a bigger atom than phosphorus, bigger atom, therefore more electrons, and therefore stronger van der Waals forces. Van der Waals forces. And stronger van der Waals forces lead to a higher boiling point. Okay, all right. So guys, that was quick. It's a good revision actually. That's a nice question because it really tests your understanding of bonding and structure. I wouldn't say it's a really difficult question, but you do need to know your stuff there. So it's a nice question to get a revision of the bonding and intermolecular forces in. I hope that you're able to do a lot of it by yourself. And the last little bit there, maybe you needed just help pointing stuff out to you. But again, this is the kind of stuff we want to see this type of question over and over again so that it's second nature, because it's stuff that comes up a lot. It's key information to help you understand properties of different substances. All right, guys, that's it. I'll see you in the next video. I hope you found this useful. I'll see you next time.